meters. Okay. And then, finally you can ask several questions actually, that when the particle is accelerating. Another kind of understanding of forward and backward movement could be that, okay, what is the period when the particle was accelerating actually? Potentially this could be the period where between 0 to 1, where the velocity is positive actually. No, velocity is positive, but for that you need to compute the acceleration. You need to check that when the particle has positive acceleration actually. So let's compute the acceleration of the particle. So the velocity of the particle was 3t square minus 90. Okay, I think yes, minus 3t square minus 12t plus 9. Okay. So what would be the acceleration of the particle? So the acceleration of the particle is going to be dv by dt. Okay. So it's going to be 16 minus equal 12. Then you can ask the question, okay, how much the particle was, for example, accelerating at, say, first second. So if I want to compute, say, a equal to 1, so you're going to get an interesting answer. So dv by dt will become 6 minus 12, so negative 6 actually. So at instant 1, the particle was not accelerating but decelerating actually. It was losing its velocity and hence become, what do you call, 0. And what would be, and hence become, what do you call, it covered no distance. What would be the, say, acceleration at instant, for example, 5 actually? So you need to have, what do you call, 18 meter per second square actually. Okay? So you're going to be 30 minus 12, so it's going to be 18 meters per second. Okay, these are the units of it actually. You can ask the question when the particle was accelerating and when the particle was decelerating. Anyway, so this is the piece of information that you can fetch out of it. So what does all this kind of stuff shows you is that how a simple idea of derivative combined with the model of position of particle can give you a lot of information about the position of the particle. Okay, and if you are, for example, in studying, say, defense systems, then all this information becomes very important for you. Or even you are in, say, aviation, you want to track, what do you call, the planes that are coming in, you want to track the position of some vehicle or whatever. All this stuff is really, what do you call, necessary. The only thing that you need a model for the position of the particle, and by model I mean an equation. Okay. Let's move to some more examples. So the next thing that we would like to, next model that we would like to discuss is what you call the model of the linear density. So density of something that is linear actually. Now we all know that the density is really the mass per unit volume for three-dimensional object, the objects that covers some volume. Okay, and it would be mass per unit length, okay, for the linear objects. Okay, so if you take a rod, if you take a wire, so you will measure its density as mass per unit length. That, okay, in a given amount of length, how much mass is there actually. Okay, so this is basic physics. So mass per unit volume or mass per unit length. Now imagine you are talking about, for example, this chalk actually. I mean, if you look at this chalk is homogeneous. It looks same wherever you touch it. So if I say, what is the mass, what is the density of this chalk at this point? So we're going to say that this is same as the density on this point or on this point. So every single point of this chalk has the same density of material in it. So it has the same density. So that would not be something interesting, okay? Because the density is constant here. While I'm interested in, for example, in a kind of a rod or a wire or something that is linear, okay, that is straight, and it has a different density. So some part of it is hard and some part of it is soft and some part of it is less soft and some part of it is very soft and so on and so forth actually. Okay, so you have a rod or something that has different kind of material attached to it at different parts actually. So imagine I have a rod. Imagine I have a rod that has some length, and imagine I'm assuming, so whenever I have to assume, for example, talk about some part of, what do you call, so if I call this as a part of the rod, so this is a part of the rod, and let's call this part has length x, then the mass inside this part of the rod that has length x would be f of x actually. So f of x is representing what? F of x is representing the mass of the rod up to the length x. Okay, so if you take a piece of it whose length is x, then f of x would be the mass of it. So obviously, what would be the density of this is going to be, f of x divided by x or whatever. So the mass divided by density, a mass divided by the length of the rod. But I am interested in what would be that if you give me, for example, two concrete points, say x1 and x2. So this was an abstract length and abstract mass. Now I'm talking about concrete. Length. So if I take, for example, x1, and what is the mass of the rod up to x1, so it's going to be f of x1, and what is the mass of say, for example, a rod up to x2, this is f of x2. But now imagine that I'm interested in, the mass of this chunk actually, this chunk only, the density of this chunk of the rod. Okay, so I'm interested in the average density in this each point of this part of the rod actually. So what I need to do, I need to compute. So this would be f of x2. So from this total mass, just get rid of this much of mass. So you're going to remain with only this mass. So f of x2 is representing this total mass, and f of x is representing this total mass. So f of x2 minus x1 will represent only this mass actually. So f of x2 minus f of x1, and everything divided by, say, x2 minus x1. So you can say this average density is change in mass divided by the change in the length, per unit length of the rod actually, per unit change in length of the rod. Okay. Now if you want, for example, instantaneous density, in other words, if I take, for example, particular position on the rod, what is really the, the density of the rod at this point? Not an interval, but at this point actually. So what you need to do, you need to bring these two closer actually. So I need to make this length shorter and shorter and shorter so that it approximates this length. So I can say the density, the instantaneous density is going to be the limit delta x approaches to 0 and delta m by delta x, and you can call it dm by dx. So this would be the density, the instantaneous density of the rod at any position of, what do you call, at any position of the rod actually. So what does this show? So this shows another interesting thing, that something that is of the material science, okay, that is of the physics, you can model it through derivative, and derivative can give you a good model or approximation for example, density. So let's take one example. Let's take m to be a function that is square root of x, and let's assume that this mass, we measure this mass in kilograms. Okay, and I want to measure, so the model for the mass of this rod at any position x is basically the square root of x. Okay, this is one model. For example, someone gave you this model, and then your task is to find the density of the particle at any position of the rod actually. And say you are talking about, so this is a model for the mass of the rod in this length actually, where say it is between 1 to 1.2. Question: what would be the average density of the rod between say 1 to 1.2? So the average density is not difficult to calculate, so you need to calculate f of 1.2 and f of 1 and 0.2. Okay? So when you calculate it, so approximately is going to be 0.48. Imagine you measure this in meters actually. So the length is being measured in meters. So it's going to be 0.48 kilogram per meter. So this is really the average density. But what would be the density? So this is average density of this rod. Okay, so it's 0.48 kilogram per meter. And what would be the instantaneous density, say at x equal to 1? So if I take exactly at this position, what is the density of the rod actually? So for that I need to calculate derivative of the mass with respect to x, and we know that how to calculate the derivative of the square root of x. So it's going to be 1 over 2 square root of x, and then substitute x equal to 1. Okay, so when you're going to substitute x equal to 1 into 1 over 2 square root of x, you're going to get 0.50 kilogram per meter, which is really closer to the average density. Okay, so this is closer to average density. So what does this example shows? That you can compute, or the derivative can be used as a model for computing the densities of what do you call the materials, of the non-homogeneous materials actually, the materials that are not of the same shape. So you're not talking about the material, for example, this table actually. This table is smooth and homogeneous at all points. Anyway, so this is something makes derivative very interesting, that the same idea can model a lot of things at the same time. For example, So I hope you are also doing a course on basic applied physics. So you must know a little bit about the current and the charge. So another model that where the derivative are being used is really, for example, electrostatics actually are electromagnetics. Electromagnetics and electrostatics are the big consumers of differential calculus. So consider a rod or a wire. Okay, so imagine this is a wire, and there is a sea of electrons that is moving. That is moving, for example, in this direction. That is moving in this direction. Now, how do we define current? So we define current as that if you take, for example, a section of this wire. Okay, so let's take this section of the wire. Okay, this surface, this section of the wire, and you want to see that in a given amount of time, in a single unit of time, how much of electrons are passing through it actually, or how much of the charge is passing through it. Okay, the quantity of charge that is passing through what you call this cross section in a given unit of the time, you're going to call it, what do you call, the current actually. Okay. So if you assume, for example, that there is a net charge that passes through, what do you call this surface is delta Q, okay, and is delta Q in delta T unit of the time, then the average current is going to be what? Is going to be delta Q by delta T. So just take the ratio of, see that how much of the charge is changing or passing through what you call this surface in a given unit of the time actually. Okay? And what would be the instantaneous current then? The instantaneous current is going to be that limit delta Q goes to 0, delta T goes to 0. So in a really tiny amount of the time, the amount of charge that passes through this surface in this tiny amount of time is going to be what you call the rate at which the charges are passing through this surface in this small amount of the time. And this is what the precise definition of the instantaneous current is. Okay. So now you can see another interesting thing that, okay, the same notion of the derivative is modeling the current. That was modeling here density, is modeling here current actually. Okay. So what you can see is that the notion of the derivative is like a beautiful tool. It's like an algorithm that you can fit it into, any situation that you like where you want to compare two things. One is dependent, another is independent. One is changing due to other. So you can model every single thing. When the things are changing due to other things, you can model that change through derivative. So that's what makes derivative very useful. For example, in chemistry, so these were some examples from physics. So let's take, say, for example, one example from chemistry. So imagine a chemical reaction. In chemistry, for example, you're talking about, say, rate of reaction. You are interested interested in say rate of reaction, so how you can model this rate of reaction. Okay. Now, what is a chemical reaction? So chemical reaction is something in which, so you take two reactants, okay, so two chemicals, and under certain condition they produce another chemical that is say a chemical C. Okay. Then you call A and B as reactants, so these are the reactants. And this chemical, this C is the product actually that is happening. So for example, one of the famous chemical reaction is that, okay, if you take two hydrogen molecule and say one oxygen molecule, then you're going to get what we call two molecules of water actually. Take the two hydrogen molecule and one oxygen molecule, you're going to get what you call the two molecules of the water. Okay. Alright, so what we want to model here. So I'm going to denote this by, for this notion, and I'm going to use this, I'm going to say this represents the concentration. This is the concentration of a reactant A in the chemical reaction. Okay. And how do you define the chemical concentration of the reactant? So you define the number of moles, okay, where we all know that 1 mole is this Avogadro number of particles, is this 6.02 into 10 raised power 23 molecules.